now that we understand free charge and bound charge, now we can get serious, okay? Let's write some serious stuff. There's not going to be any drawings here. This is just serious, this is serious stuff. If free charge is placed near a dielectric and induces bound charge the total uncancelled, I'll say, charge is what? It's just rho total equals rho bound plus rho free. And they could be sigmas if they're surface charges. But let's assume for now that they're volume charges. All I'm saying is free charge is clearly excess charge. And rho bound, that's why I meant uncancelled. Right? So the dielectric is neutral, but if its charge gets shifted around, you might have some places where it shows up, either on the surface or in the bulk. That's what we've been talking about. So now we have a statement of the total charge. But now what are we doing? Why do we do this? Okay, I'll lie. I'll do one more. Okay. Why did we do this? We had a dielectric sphere, right? And we're going to put in a charge. I'm not even going to put it in the middle. I'm going crazy, okay? It's going to create a polarization field. You're going to get bound charge in here. You're going to get bound charge on the surface. You got your free charge here. What we really want to do is calculate the electric field. We want to calculate the electric field in the material, out of the material. It's going to respond funny. We want to figure all that out. Well, when you want to calculate the electric field, the most powerful way to do it is Gauss's law. Okay? So we're going to take this and stick it in Gauss's law and see what happens. Okay? So whenever you want the electric field, apply Gauss's law. And Gauss's law does not care about external fields and internal fields and who created what and superposition of all those fields. No, Gauss's law just calculates the E field. So we're leaving all those subscripts off. Now when I say the E field, I mean the actual E field. I mean that if we took a test charge and put it in that region and ignored all the molecular structure, F equals QE. This is telling you the force on that test charge. Okay, that's the only electric field that we care about. Okay, Gauss's law. The integral closed surface E dot dA equals what? It equals the charge enclosed over epsilon naught. So here is our total charge enclosed in that surface, rho bound plus rho free. And when those are written as charge densities, you just have to write them as integrals. 1 over epsilon naught, the integral over the volume of rho free dV, plus 1 over epsilon naught, the integral of rho bound dV. Right? That's really just Q enclosed over epsilon naught. Just the two flavors of Q enclosed, the bound and the free. Okay. Now let's write it again. The integral around this closed surface of E dot dA, and we're going to change one of them. Let's leave this one, 1 over epsilon naught integral of rho free dV, and then this one, remember what was rho bound? It was minus the divergence of big P. Right, so we could write this as 1 over epsilon naught, the integral of minus the divergence of the P. Right? We're trying to work on this in terms of fields. Okay? And now let's apply the divergence theorem. This is real field theory now. What was the divergence theorem? That was, I always like to say it. How was it I like to say it? The integral of a derivative over a region is related to the value at the boundaries. Right? All the theorems of calculus, that's really what they are. This is the integral of a derivative over a region is related to the value at the boundaries. So instead of this integral of this divergence, which is a derivative in a volume, we're going to turn that into a surface integral of P. That's what the divergence theorem does. So we still got this part the same, the integral around a surface of E dot dA, and we still have this part, 1 over epsilon naught, the integral of the free charge, dV. But then the negative sign is going to stay, and it's going to become minus 1 over epsilon naught, the integral of P dot dA. Right? The integral of a derivative in a region is related to the value at the boundary. Okay, we've turned it into that. Well, now if we look, we see that these are the same integral. They're over the same closed surface, and one is E and one is P. So we can bring this over here and say it's the integral around the closed surface of E plus, so we also have to multiply through by epsilon naught, epsilon naught E plus P plus P, right, equals the integral of rho free dV. So the epsilon naughts went away. And this is actually the useful way to apply Gauss's law to find the electric field. But what we do is we give this a new name. This is what we call D. Ugh, that's a terrible looking D. This is the displacement field. The displacement field has always bothered me. It seems so unnecessary. Why do we need to make up a third field? We already have the electric field, we already have the polarization. Can't we just call this always epsilon naught E plus P? Do we have to call it D? Is there some intuitive meaning of the displacement field? I don't think there is. It's very useful to solve problems, and I'll show you in a minute we'll solve a problem. But I think if you look at Maxwell's original paper, he just labeled the fields A, B, C, D, E, F, G, H. Right? And then he had some nomenclature that nobody uses anymore. And then Heaviside and I think Hertz or someone gave us the modern version. And I think they kept D and called it displacement, but I think of it as it displaces a lot of work you would have to do keeping up with things. That's my definition of the displacement field. So you're going to see in a minute, though, why it's useful.